Greetings, this is Eugene the Philosopher, the greatest living philosopher after the unfortunate passing of Quentin Robert de Nameland, who has been the greatest living philosopher before me. Let us talk about explanations and theories in general. And I really hope that this video is going to be shorter than my average videos, but we'll see. Like, if I wouldn't be distracted by flashbacks from Peloponnesian War or something, which often happens in those videos, as you know, it will be a short video. Okay, so first of all, let me remind you some of the things I've talked about previously. In particular, in my video, Nature of Knowledge, I discussed that, well, really any knowledge is just a bunch of stories that we tell each other about the world, right? So in this video, I wish to sort of enhance a little bit on this statement and talk about explanation, like what it means to explain something to somebody, including yourself. So I would say, and this is probably the main point of this whole video, that explanation is really an act of translation, if you like, of one story to the other. So in some sense, we just map one story and actors of one story onto the actors in another story, or we establish a correspondence, if you like, between those two stories. And this is really the main point I wish to make in this video, so I guess we might wrap up here already, but still, I have some other points I wish to make here. Like, in particular, well, let's examine the details of this process, of this mapping. So in order to achieve that, a narrator, a person who tells those stories, needs to construct certain objects, right? So we construct a set of objects which we believe would be a good in good correspondence to the objects of another story that we're trying to explain. So this is basically what we're doing. And well, it's not very hard to come up with an example. Like, you might think about, well, this model of an atom or a particle in general, which is frequently depicted as a solid ball, you know. So any sort of behavior of macroscopic systems, according to modern understanding, might be boiled down to the collisions of those solid spheres or something like that, or some other types of interactions between them. So there you go. This is the explanation of macroscopic phenomena through, like we observe, like heat. This is one story, right? So something is hot, something is cold, etc. So this is one story. And another story is we have a bunch of solid balls colliding with each other, right? This is another story. And we try to establish correspondence between them. And in particular, like molecular kinetic theory does exactly that. So there you go. This is how it works. And it's not hard to notice that any physical model is exactly that. It's simply an attempt to translate one story into the other. From, if you like, one language into the other language, right? Or something like that. So physicists, at least smart physicists, know and recognize really well that they work with models. They don't work with reality, whatever the heck that is. In some sense, physics works with virtual reality, you know, this alternative type of story that we substitute the original story with or for, whatever. So we just pretend we're talking about this thing, but instead we're going to talk about this thing, right? So this is what physical model is in a nutshell. And due to this fact, or at least partly due to this fact, I believe the method of analogy is so popular in physics because, well, this is exactly that, a translation, right? So we have one system where we already know how it behaves. So we have one really well established story that we are confident with, and we try to sort of just simply use the same type of story in another type of physical system. So this is what analogy is all about, and sometimes it works really well. So then, yeah, so in some sense we have explained this other unknown system with our already known system, right? So this is what explanation is all about, and in physics in particular. And mathematics obviously helps here a lot because, well, mathematics itself is a very abstract language. So it sort of tells you things about many things simultaneously, but none of the particular things at the same time, right? So it sort of says things about something which isn't defined, you know, so you can easily use mathematics to translate one type of story into the other type of story, right? Just exactly because it's so fruitless, so to speak. It's so barren. It doesn't tell you anything about anything in particular, but it tells you something about everything, you know, in some sense. So it's this universal language of sorts. So it works really well in physics. Okay, so one question we might ask is this type of translation always possible? Because, and it's a really good question, I would say, because, well, my point would be that it's not guaranteed that you can always translate one story to the other or vice versa. So explanation is probably not always possible, even. Like, in the most general sense, I would say that, yeah, it's almost like impossible. But in some cases it is possible, at least it seems so. But anyway, it is really hard to prove relevance of one story to the other, like the possibility of establishing this correspondence between them, right? And it's sort of obvious in astrophysics and cosmology, and perhaps particle physics too, where we're dealing with systems, or rather objects and relations between them that are so removed from our everyday experience that our conceptions, our concepts and ideas and the sorts of objects we're used to be dealing with no longer work, right? So we have to invent some additional weird objects, like, for example, if we're talking about particle physics, well, obviously we had to invent things like quantum mechanics to deal with them, which is quantum mechanics. It's so different with respect to our everyday experience that, yeah, well, there you go. So we've had to produce this super artificial, super wrong sort of thing to be able to translate the observations into some model, which in this case is a quantum physical model. And it's quite interesting that on the other end of this spectrum, in astrophysical realm and cosmological realm, we don't really have a theory like quantum mechanics. Now, you might say, well, it's relativity theory, but I wouldn't say so. Like relativity theory doesn't really contradict your intuition, if you like. Well, or rather, like, my point here would be that it doesn't really work with anything new in some sense, you know, like all these paradoxes of relativity, they aren't really specific for like super macroscopic scales. Like in some sense they're specific because, well, general relativity effects only appear when you have strong gravitational fields or something like that. But that's a whole separate issue, I believe. So there is no macroscopic quantum mechanics, or at least an analogy of quantum mechanics in macroscopic scale. But okay, I don't really want to sort of push this notion too far, push this statement, or explore it. It's just an observation that I've had, probably, you might say. Okay, so and another point I wanted to make is that, like, simple translations are dubious in their, again, validity, you might say. Well, when people just say, well, objects, let's say, in space behave the same as objects on the Earth, let's say in our laboratories, it's a very strong statement, and it's an understandable statement because we just want to subdue the world, so to speak. We want to, again, will to power. We want to establish our control over the world, so we just force the world to behave, well, in some sense, as we like it to behave, right? So we say, well, in space, there's pretty much the same types of objects as the ones that we can observe on Earth. So we say that, yeah, well, space is governed by gravity, electromagnetism, etc. But it's a very ill-founded statement, I would say. Like it doesn't follow from anywhere except our desire for it to be so. So it's kind of dangerous, I believe, in this sense. So when people say that, oh, again, this is sort of a hand wave to my friends from Electric Universe community, that if we say that, oh, the sun is electric, well, what the hell does that mean? Well, can you just translate the laws of electromagnetism that we have here to the sun and just like depict it as a simple object that you can observe in laboratory? It's very dubious, really. Like, it doesn't seem to be founded in anything, really. Okay, so these simplistic translations seem dubious. That's my point here, basically. And well, even our concept of 4 fundamental interactions is also dubious in this same regard, because, well, why is there only 4? Well, actually, there's kind of 5 fundamental interactions, because we also have Higgs field, or at least supposedly we do. And it's also sort of ill-founded, like why do we suppose that it's that simple, that there is only, let's say, 4 different stories, let's say how would you say it, like the collective workings of which would produce everything that we observe? That doesn't really seem to be the case. That would be my point. Like, it's too simplified. It seems so. So it constantly produces all kinds of artifacts and errors, right? And, well, in this regard, I wish to talk about some other things, like I'll just give you an example, and then I'll sort of ask a generalized question following from this example. So at one point, again, in all those Electric Universe communities, I've stumbled upon an interesting question, or rather an interesting statement maybe by someone. I don't really remember who said that, but what they said was that, well, how would you explain electric charge? Like, what is electric charge? How does it appear? And I was instantly baffled by this question, because, well, think about what electric charge is basically, this story about electric charge only involves 2 actors, if you like, and 2 relationships between those actors. So the 2 actors that we have is negative charge and positive charge, and relationships between them is that like charges repel and opposite charges attract, right? So that's 2 objects and 2 relations between them. So my general question with regards to this would be, if you want to explain how charges appear, like isn't that already simple enough? Like 2 charges and 2 relations, 2 objects and 2 relations. Like, how much more simple do you expect it to be? Like, where do you want to go with that? Like how into what simplistic story you want to turn this into? Because, well, it looks very simple already. Like, you might say, well, theoretically at least, well, let us say that, just for simplicity, let us say that positive charge might be produced by negative charge. So it's some complex behavior of negative charge that produces positive charge, right? So that would be sort of like simplification, because now we only end up with one fundamental object, which is the negative charge. But at the same time, we sacrifice the simplicity of relationships between objects. So now we have to introduce a third interrelation, you might say, like you need to introduce a mechanism through which a negative charge would produce a positive charge. So you end up still with the same four entities, essentially. So initially we've had two objects and two relations, and now you have one object but three relations. So there would be a negative charge as a fundamental object, plus a way of how negative charge produces positive charge, that's the second entity, and plus the two other entities that we've already discussed, that like charges repel and opposite charges attract, right? So is it any better to have one object and three relations versus two objects and two relations? Or you might say, well, both negative and positive charges are produced by something else. Well, now you introduce something else plus two relations, which, like something else producing negative charge and something else producing positive charge. So you end up with 5 entities instead of 4. Is that a good thing? Is that a simplification of anything? Well, I heavily doubt that. So it's a thing to look into, like how much, like where's the limit of simplicity, you know? You probably shouldn't aim at multiplying entities, you know, Occam's razor and all kinds of things like that. So it seems like in many cases, like in this case, number of elements plus the number of their relationships seem to be like more or less constant, or at least you should keep it at a minimum, basically. You always can introduce many more objects and many more relations, but is it helpful? Is it fruitful? Well, that's a different question, and that's an important question, I believe. Okay, I've probably ranted enough about this. But yeah, so you always, basically that's sort of my point here, you always sacrifice simplicity of relationships of objects if you tend to reduce the number of objects. So you have to introduce additional relationships always if you try to reduce the number of objects, or like internal complexity of objects increases. So you might pack a lot of relationships into a single object, or you might treat them as separate objects, right? So these are two different, I guess, approaches to describing things. And physics tends to actually reduce the number of objects and increase the number of relationships or properties of objects. This is easily seen, like, again, in one of my previous videos, I've given the example of Maxwell's equations, how, again, well, if you look at Maxwell's equations per se, there are like 16 equations or something like that, or at least 12. But Heaviside reduced them into 4 equations, but we've had to sacrifice simplicity of each separate object in those equations, right? So a vector is 3 components, right? So if you have 4 vector equations, well, each element of them, each vector is extra complicated because of that, right? Or we might actually in covariant form formulate Maxwell's equations just like one equation, at least in Lorentz gauge, as like this D'Alembert operator acting on 4 potential equals 4 current, well, multiplied by like this permittivity or something. So you have literally one equation, but each term in this equation is incredibly complex. It's like a whole pantheon of other concepts and other entities right there, sort of just condensed into a single entity. So it's not really a simplification, like it's simplification in some sense, but still to work with this, you would have to unwrap all that, you know. And again, the same story is with Higgs field, which really only complicates things. Like, well, imagine we had 100 particles with 100 mass constants, but now we introduce Higgs mechanism for producing these masses, and we have extra object, 101st, I guess, which is the Higgs field, and we have 100 constants of interaction of Higgs field with each separate particle. So now we have 101 entity instead of 100 entities previously, right? So is it any better? Like, it doesn't seem so, I would say. So Higgs field is rubbish. This is my point. Okay, so yeah, so I guess we've talked about this enough. But again, hopefully you can see where physics is going. It's trying to reduce the number of objects by paying that, so to speak, damn, how do you formulate this? So in favor of having more relationships or more complexity of each single object, basically. Okay, so all right, and another point I wanted to make here, because it seems relevant, is that really any formula, any physical formula, is really a hypertext, if you think about it. Because, well, any equation, it contains, well, again, those mathematical symbols of like mass, force, acceleration, electric charge, current, whatever. So each one of those references some other concepts. So really any equation is like a HTML page, you know, so you can click on the mass and it would take you to the page of the mass, so to speak. So, but the formula itself is all of those things condensed in a single entity, right? And I haven't heard anyone speak about hypertextuality of formulas, and I think it's an important thing to understand, that they are really like entities which might be named hypertext. All right. Okay, so let us talk about the theory of everything, like this problem of formulating a theory for everything simultaneously. And again, the same question might be asked, like, why do we think it is justified? Why do we think that a single story might be told which would fit everything, like all the observations in the world? Like, firstly, it's not guaranteed that it is possible, right? But secondly, and even more importantly, there's another limitation here, because, well, what I would say is that any story needs a focus, what I've called framing in my video about stories of history. So, and what is focus? Well, literally, it's the same as in optics. You sort of magnify certain elements, but you sort of ignore all the other elements, or like seriously distort them, right? So you just isolate what you are interested in, and you just completely ignore everything else. So that's what any story is all about, essentially. And physical theories are also stories, so it's also relevant for them. So they should do the same thing. But if you're aiming at having a theory of everything, it means you're kind of defocused. You're kind of aiming at everything at the same time. You cannot ignore anything, right? And it's easily seen, it can be easily seen that it is pointless, because, well, theory of everything would not be able to distinguish stuff. So, in some sense, you might say that the most universal story you can come up with is also the most irrelevant story at the same time. Because it talks about everything simultaneously, and it doesn't allow us to operate, because we need to distinguish stuff. Because, well, my hand isn't the same as this chair, and it isn't the same as this curtain, etc. It isn't the same as the light falling onto my face, right? So we need to distinguish between all of that. But if you have a theory of everything which describes all of that simultaneously, it's pointless, right? It's impractical, absolutely impractical, and absolutely irrelevant. It's relevant for everything, and therefore it's not relevant for anything. That would be my point. It's like pure chaos, or pure void, something like that. Like, I can give you an example of a theory of everything. It would literally describe everything, and it would sound like stuff exists. It literally, it's fitting for everything, and therefore it's absolutely irrelevant. Like so what? Like, yeah, stuff exists, so what? So that's more or less what I'm talking about here. And It kind of reminds me about this problem of universal solvent. You know, the alchemy, Paracelsus in 1500s came up with this concept of universal solvent, which is also called alkahest. And it, by the way, it also shows you that alchemy, history of alchemy is completely made up. Like, if only in 1500s people came up with concepts like that, like what have they been doing for the previous like thousands of years? So really alchemy probably appeared only like 15th century at best. But anyway, so it took additional 100 years for people to realize that this concept is super stupid, just like the theory of everything concept. So a guy named Johann Kuhnkel from what is modern Switzerland, let's say, he noticed that some contradictions, let's say, in this concept of alkahest. So he said, well, guys, wait a minute, like, if this substance, whatever the heck it is going to dissolve everything, well, it's a universal solvent by definition, it's also going to dissolve the vessel it is contained in. So how are we going to contain it? So it would be, you know, it would melt all the way to China, so to speak, referencing this famous China syndrome. So it's pointless, right? Such a thing cannot exist. Yeah, fair enough, I would say. Well, like you might say, well, what if we ionize it and then like magnetically confine it or do something like that? Well, that's a whole separate discussion. But anyway, yeah, I think it's a good illustration about all those super general statements and objects, right? And at the same time, it's an illustration that the history of alchemy is rubbish. Okay, so one other thing I wanted to talk about is this woman, Cohlfurey, Cohlfurey. You might find some of her videos on YouTube. So she became famous recently, in the recent few years, when she, well, since she talked about the four division algebras, what is called division algebras, in particular, and those are the algebras where you can add, subtract, multiply, and divide, right? And there are only four of them known, and those are, well, I'm sort of simplifying here. I'm not using the strict terminology, but those algebras are acting on sets of real numbers, complex numbers, quaternions, and octonions. So these are the four division algebras. And apparently, according to her, this realization would somehow help us build a theory of everything, or like at least enhance our standard model of particle physics. But I would say that, well, again, it's a pointless statement in some sense. Like, if we have in mathematics those four self-consistent systems, if you like, these division algebras, well, what does it really tell us? Well, yes, you might say any sort of theory would be, or at least might be, formulated using those four. Okay, well, that's a good statement, but so what? Like, it doesn't tell you what exact theory you should have or would have, right? So, and let me give you an analogy to sort of better understand my disappointment, so to speak, with those kinds of statements. So, since mathematics is just a language, as I've stated many times, it doesn't give you any sort of door to transcendent, you know. It's just a language. So making a statement that those four division algebras would contain the theory of everything, or the theory of everything would be formulated using four of those, is just the same as analyzing the regular language, the verbal language, or however you wish to call it, and noticing that verbal language can be dissolved or disintegrated, so to speak, into nouns, verbs, adverbs, and adjectives, or something like that, and concluding from that the theory of everything would be formulated using nouns, verbs, adverbs, and adjectives. Like, yeah, but it's a trivial statement. Like, it doesn't tell you anything. It doesn't lead anywhere, you know. It's a tautology fundamentally. So yeah, unfortunately, this important realization probably is not going to lead anywhere. But okay. Plus, you still have all the problems with theory of everything that I've stated before. All right. And another thing I wanted to mention is that we actually, at some point, studying all those problems, we might arrive at a horrible realization that any kind of explanation, all kinds of explanations are equal in some very fundamental sense, because it doesn't really matter what kind of story you are building a correspondence with to some other story. So if you have one story, let's say the sun shines or something like that, and it doesn't really matter what kind of other story you're trying to translate it into. So it might matter in some practical sense, like some stories would allow you to do some other things, but fundamentally all those explanations, all those translations are equal, I would say. And this is the thing that I've mentioned in my video about Copernicus. Is this over already? Okay, so in my video about Copernicus, so I talked about this idea of Einstein and Infeld, who said that, well, there is no fundamental difference between geocentric and heliocentric systems, frames of reference. They are fundamentally equivalent. So, and this is the same kind of realization that we have in general, that any sort of theory is possible, and all of them are equal in some, again, very fundamental sense. So I guess here we're getting rid of this dream, of this sort of wet fantasy of scientists to uncover the theory, you know. Trying to, it's almost like, I would have this analogy that, again, uncovering the theory of everything is almost like trying to write a theatrical play, which would simultaneously contain all kinds of plays, all plays, all the possible plays, right? And it makes no sense. Such a play would be pointless and devoid of content. Again, it would talk about everything simultaneously and nothing specifically, right? And speaking about the analogy between theater and physics, well, I've already touched on this subject in my video about bad ending, so you might look it up if you're interested in this. But yeah, there is definitely an analogy. Like a play in a theater is like, again, it's a story. So it's very similar to the types of stories we have in physics. We have objects and their relationships and their behavior, etc., etc. And in theater we have people and their behavior and their relationships. Okay, so probably one last thing I wish to discuss is that, well, I wish to make like a wish or well, I don't know the proper word, but I wish to express my desire towards alternative scientists, you know, or pseudoscientists. So, but let me try to segue into it. So, my statement here would be that simple ideas, like let's say we have some simple alternative theory that XYZ is not alpha, beta, gamma, but they are I don't know, pick 3 other letters, R, Q, S, whatever. So we have some alternative theory, right? But I would say that they only look simple because they are underdeveloped. So this idea of Imre Lakatos, that a theory builds this, what he called the belt of protective hypotheses around it as it struggles to explain reality, let's say. So this idea might be reinterpreted in a positive sense. You might say that it's an inevitable process, that you start with a simple theory, a simple story, but then you observe reality, and it has all kinds of other stories that you have to keep translating into your simple story. And your simple story becomes not so simple anymore. It has to build other supportive stories that would explain those additional observations, right? This is what I'm talking about. So basically, simplistic models always produce those artifacts, errors, and inconsistencies. In the programming language, you might say they keep throwing exceptions, like returning errors, etc. So, and again, this is my desire towards these alternative scientists who apparently invent some simpler models for something that has another model which is sort of overgrown itself, so it has all those additional hypotheses, all those crutches to be able to exist. But they propose a simpler model that would apparently be better, at least in some respects. So my desire is that if you attack an established model with your simpler model, at least one thing you should do is to be able to reproduce all the good stuff that this established model is able to do. So you should be able to explain all the things that it is able to explain, however complicated it is. Like, most of the time, it comes from my experience, what I see is that people propose a simple model, simple alternative model, but they don't even explain even 1/3 of all the things that are explained by this more complicated model. Like, most of the time, they only aim at certain specific observations which are really poorly explained by the established model. So their model really explains this really well. Like this mapping is much better, right? This translation, explanation. But unfortunately, they somehow ignore everything else. And they say, well, it would follow later. Like, we would find ways to explain this. Well, certainly you would. But you would also need to overcomplicate your own simplistic model to do that. So this is what I'm saying. And yeah. So simple models are not as good as they look on the surface, because most likely they wouldn't be able to explain even 1/2 of what a more complex model is able to explain. So it's important to remember that. And if, let's say, you're trying to get rid of quantum mechanics and you're trying to come up with some other theory which would be better, well, at least you should be able to have the same results as quantum mechanics does. In all the respects, in all those thousands of effects we know from quantum mechanics. And it's almost, well, it's actually never being done. That's my point. And this is sort of, it makes it understandable why new theories are so hard to be adapted, by the community, by the scientific community. Well, it's not because the community is evil, although this is also the case in many respects. I mean, see my videos about sociology of science, about Einstein and Hawking, about science and anarchy, well, all those videos basically. So, but it's also a problem that new theories, simple theories, they're not as good in a literal sense. They are much weaker in many respects. But okay, I probably ranted about it enough. One other thing, probably one last thing I wish to mention is that there's a good video by Richard, or at least with Richard Feynman, and you might easily find it on YouTube. You might just search for Richard Feynman Why. So it's like 7 minutes long, where he also explores this idea of what it means to explain something. Like, and his point is that you should have some limit, to your explanation. Like, where is the point where you're going to be satisfied with an explanation? So you have to start with some basic concepts and stories to which you're going to reduce whatever you're trying to explain, right? So when you've reached this level, you're satisfied and you say, okay, that's enough, you've explained this to me. But unfortunately, and this is sort of the statement he makes, although I'm sort of generalizing what he said, because he talks about particular examples there, but you can also translate these fundamental stories into something else. So, and there's no limit to that. You might go deeper and deeper into everything, and again, there's no fundamental limit to that. So this is one of other points I wish to make here. And returning to the issue of the theory of everything, well, there's obviously things like Gödel's theorem, that you cannot actually have a self-sufficient semiotic system, symbolic system, that would explain everything and would not require explanation of itself, so to speak. So that's another big problem. And again, well, you might try to deconstruct Gödel's theorem in the first place, because it's also just a story, and it's based on other stories, on mathematical stories in particular, but okay, that would be a whole other story, so to speak. All right, so what we talked about in this video was that my statement that the explanation is the act of translation of one story to the other, establishment of this correspondence, right? That this correspondence is not always possible. Like it's really only our desire to make it possible, right? But it's not guaranteed that it would be possible, and therefore the failure of this translation would lead to a necessity of producing additional stories in support of this simpler story that we've translated the observations into initially. All right. Then another point I've made in this video is that there should be a certain limit to simplicity of a story. Again, see my example with electric charge. There is a certain elasticity, if you like. You cannot go further than some limit. It would kind of bounce you backwards, so to speak. So we would have to invent additional complications on top of your simpler model. And it also concerns all those new theories, alternative science, etc., that it's really only simple. It allows itself to be simple because it's very weak and it's unable to explain many things, because, well, the authors of these theories, they apparently think that people should just, cherish them as they are, even though they haven't contributed anything useful. They haven't explained anything extra, and even all the other things that are already explained, they don't explain them. Okay, and another thing I made here in this video is that really all kinds of explanations are equivalent, and it's just a matter of taste, really. It's a matter of what kind of story you would consider what's the right word, like plausible, I guess, or like preferential with respect to other explanations. But it's your personal opinion that's involved here, right? Or some other, well, yeah, basically your value system. Like, if you say, even the statements like we should prefer simpler models to more complex ones, was that formulated correctly? So we should prefer simpler models. Let's stop here. Even statements like that are based on your value system, because, well, you say that, well, simpler model is better, but why? This is a completely arbitrary statement, right? So there you go. And the other issue I've discussed is the theory of everything. So my point is that it's pointless because it talks about everything simultaneously, so nothing in particular. So it describes everything while not describing anything. And it's absolutely impractical because we need to distinguish between different things. And theory of everything, whatever the heck that is, would be unable to do that. So it's pointless. Like let's just forget about it. It's a really stupid idea. Okay, so probably that's enough for today. Thank you for watching. The eons are closing.